Recording in progress.
Good morning.
Morning.
Hi, Chris. Well, I can feel the end of the semester approaching rapidly. We're at the end of week 14, so we just got 2 more weeks, which means we got to get things wrapped up so that we can go into the 16th week. That's our finals week, being able to kind of look at all of the work you've done over the semester. So that's what's coming up over the next couple of weeks. Is I'm going to be putting up pretty soon, hopefully over the weekend, a sign up, basically a form you can fill out where you can pick a time slot to meet with me during that 16th week. It's just going to be a quick, about a 5-minute Zoom session where we just go over all the work you've done. I take a look at a survey form that you filled out, and we arrive at a consensus about what your grade ought to be that I submit for your transcript. So I would say when you fill out that form, I would give it about half an hour to fill out that form, because I'm going to ask you to go through your list of assignments and take a look at them, and then be a judge as to the quality of the assignments. I'm not so much interested in the quantity, although the quantity does factor into it, but I'm more interested in the quality. Did you learn over the semester? Did you mature as a student? Did you develop some new skills, and were you able to apply those skills outside of the classroom? So that's the kinds of things I'm looking for in that survey. So again, take about half an hour to fill that out. Let me shut off this music here. There we go. So as far as the remaining assignment to do, it's just a very simple program to measure the round trip time it takes a packet to travel across the internet and come back. Let's take a look at the assignment really quickly. And actually, if you click into the assignment, I've actually got a video that you can watch up at the top of the assignment. So I'm not going to get into all of the same details that the video gets into. I want you to watch that instead. But let me just quickly go over the assignment. So you are going to download, compile, and install that libsocket library we've been using for the past week. There's instructions on how to do that. Plus we did that, what was it, last week? So you can follow along in the live session. So what is round trip time? Whenever you send a packet of data across the internet, it takes some time to get there. And then usually the computer that's on the other end will respond to that information. So in a client server setup, the client is going to send a request over to the server, and the server is going to respond with the requested information. And so what we're trying to measure is the total amount of time it takes that packet to go over to the server and come back. So I've set up a server in several places around the world, and they're all listening on port 5055. So I just picked that number kind of randomly. There's nothing special about that number. Once you connect to port 5055, the server will just read in a line of data from the client. It doesn't matter really what you send. You could probably send something really small, like just a single character. And then you'll get back two numbers. You'll get back a counter, which is just incrementing as I send data. So it just goes 1, 2, 3, 4, 5. And also it sends back the length of the line that was sent. Those are very simple. The response just serves as a confirmation that it received your request. So the server is not going to give you back a document. It's not going to give you back any kind of anything special. It's just going to give you back two numbers. The idea is that the response is just really short. So all your program is fairly simple. It opens on a connection to one of the servers I set up, and there's one in Fremont, California, London, Mumbai, India, Sydney, Australia, and Newark, New Jersey. So they're scattered all around the world. You send a line of data, and it receives the response and gives you back those two numbers. What you need to do is measure the total time that it took. So to measure time, there is a function called get time of day, and you're going to pass it one of these structures to fill in. And the structure contains two values in it. The number of seconds since January 1st, 1970. So according to Unix or Linux computers, that's when time began. It began on January 1st, 1970. So it gives you back the number of seconds, And then within that second, it gives you back the number of microseconds. A microsecond is a millionth of a second. So these are not two separate measurements of the same time. This measurement up here is incrementing once per second. And this measurement here is incrementing once every millionth of a second, and it rolls over every second. Okay? And I'm saying this because I've had quite a few students who have tried to do this program in the past and simply only look at this field, thinking that that's the number of microseconds since January 1st, 1970, and it's not. It's the number of microseconds since this second began. So every second, this counts up to 1 million and then rolls back to 0, and then counts up to 1 million again and then rolls back to 0. So here's a short program that'll display the current time in seconds and microseconds since January 1st, 1970. You create a structure, then call get time of day. And then what you do is you take the number of seconds and the number of microseconds. You're going to take the number of microseconds, you're going to divide that by 1 million so that that becomes a floating point number, and then just add those two things together. And then you should get a floating point number or a double number that represents the number of seconds since January 1st, 1970 down to the microsecond. Let's go ahead and try this program. So this just spits out one number. It's been 1,651,768,647.838005 microseconds or seconds since January 1st, 1970. And so if I run this again, you can see that the number of seconds has gone up. But in this case, the number of microseconds has gone down because I'm not running it at exactly the same moment. So every time I call this program, I get the current time in seconds down to the nearest microsecond since January 1st, 1970. So what we're trying to do is measure the amount of time it takes to send and receive some data across the internet. So what you're going to do is fetch the current time, so use some little piece of that program that I just showed you, store the time in a variable, send data to the server, receive the response, fetch the time again, storing in a different variable, and then subtract those two times. And that will give you the interval, the number of seconds down to the nearest microsecond since you sent and received the data. So try not to include the time it takes to open and close the connection. We're not interested in that. We're only interested in the time it takes to send and receive a request and response. Okay, so do that 3 times, and then you'll want to average those 3 times to get an average round trip time. So here's what the output of the program might look like. Here's the name of the program, and then here's the server we're going to connect to. You're going to take the name of the server the user types in and tack on .cs.sierracollege.edu, and that'll give you the complete host name that you're connecting to. And then it sends a packet, receives one, sends, receives, closes the connection, and then averages those times to come up with an average round trip time. Last thing I want to point out is that the first response usually takes a little extra time to do, and that's because the server's got a little bit of housekeeping to do. And so what you'll probably want to do to get a more accurate reading is after you open the connection, just have your program wait for a second. And that'll give the server end a little time to settle down, and then start your measurements. So you can do that very easily. You just add sleep 1 in your program. So after you make the connection, put your program to sleep for a second, and then start sending and receiving your data. You'll need this header file to be able to use the sleep function. So a very quick way to get your program to just pause for a second. What you're going to turn in is, since this is such a simple program, there's no need to put it into version control. You're just going to upload the C file, and you're also going to upload a text file that contains the output of your program, and I want you to run it on several of the servers around the world, showing all the different times. So by the way, here is an actual run of the program to the Sydney server. And the machine that you're running your virtual machine on is in Fremont, California. So it's somewhere near San Francisco. And according to this, it takes a total of about 182, 187 milliseconds to make that round trip to Sydney. Now the question is, how fast is that in relation to other things? Like maybe, how many miles per hour is that? So how would we measure that? How would we figure out how many miles per hour the data is taking to go all the way to Sydney and come all the way back from Fremont? So let me bring up a picture of the world here. So here's Fremont, and Sydney is like over here, and it's probably not going this way to go across. It's probably going, off the map and wrapping around and then coming this way. And how does it get there? Well, you probably know that crisscrossing all the oceans of the world are these fiber optic and wire cables running under the ocean. And so the data packet leaves the data center in Fremont, and then it enters one of these undersea cables, and then starts, goes past Hawaii probably, and then comes this way down towards Sydney. And, who knows, maybe there is a more or less direct connection between the west coast of California and the east coast of Australia. So it probably does not maybe like go to Hawaii and then from there go to, whatever these islands are over here, and then to Sydney. Probably, since Sydney is such a big city and the Bay Area of California is also a big metropolitan area, there's probably a direct connection between those two cities. So what we need to do is figure out what's the distance that we think that the data is traveling through. So how can we figure out how far it is from Fremont to Sydney? Any ideas? Well, maybe we can just ask Google. How far from Fremont, California to Sydney, Australia? And it says it is 7,432 miles. So let's go with that calculation, that estimate. Let me get my iPad going here. So Google says that this is 7,432 miles. It takes 180, let's just go with 185 milliseconds round trip. So if here is, and I'm a terrible artist here, but here's the United States, you know, and here's Australia. And then there goes our line from there to there. It takes 185 milliseconds to make that round trip. So how do we do this calculation? I'm asking you, how do you do this calculation? How can we figure out how fast is the data traveling?
So I think we'd start off by dividing the total miles by the total milliseconds. That'll tell us miles per millisecond. And then we have to convert the milliseconds to hours.
Now you're almost right there, Chris. We have a little bit of an adjustment to make. This distance, 7432, is the one-way distance from Fremont to Australia. But this time is the two-way distance. So one of these needs to be adjusted. Either we need to double the distance, or we need to halve the time.
Yeah, so I guess truly it's double the distance.
Okay, so let's double the distance instead.
Going both directions within that time.
$7,432 times 2 is 14864. All right, so 14864 divided by 185 gives us 80.3459 miles per millisecond. But we need to convert that into miles per hour. And those of us who are not watching in the United States are like, what the heck is a mile per hour? But this is what we're going with. Okay, so how do we convert this to hours? So we're going to have to, let's see, what did they call, I learned this technique in my science classes. That if you got 80.3459 miles per millisecond, then you need to multiply that by something that starts converting that.
So the numerator would be 1 millisecond.
Mm-hmm.
And then the denominator would be 1,000 times 60 times 60.
Oops, this is actually not right. It's not 1 millisecond per 1,000 seconds. It's 1,000 milliseconds per second.
Oh, okay.
So there's 1,000 milliseconds per second. And then
the next one would
so
be,
the idea is that we want these like units to cancel, right?
Right. So 60 seconds per minute. And then 60 minutes per hour.
Okay, so what this suggests to us that we need to take this number and multiply by 1,000, then multiply by 60, and multiply by 60. Oh, you know what? I'm looking at the number here going, whoa, that is way bigger than I thought. And the answer is because usually the speed of light, well, this is miles per hour, but this is kind of a nonsensical number because it's just so big. But we probably want just miles per second. because the speed of light is measured in miles per second. So let's just go with that. So let's not do this conversion into hours. Let's just leave it at seconds. So we're looking at 80,345 miles per second. And the speed of light equals 186,000 miles per second in a vacuum. So if you compare these two numbers, it looks like the data is flowing at roughly half, a little bit less than half the speed of light, which by itself I think is an incredible number, because the data is coming out of the computer and it's going through a series of network connections inside of the data center until it finally finds its way to the undersea cable, and then it goes through that at the speed of light, probably goes through another series of network switches and routers until it finally finds its way to the data center in Sydney, and then it has to reverse that whole process and come back again. And it does that all at half the speed of light, which I think, is an incredible number to have, like, all this computational resources working in concert to get that data out of one computer and into another computer across the whole world and then back again at half the speed of light. And actually we can find out, like, all the steps it goes through. If I say Traceroute, is that a program I got here? No. Let me install that. Got a bunch of errors. No, let's try this. Oh, here we go. So Traceroute, sydney.cs.sierracollege.edu. This is a nice diagnostic program that is used to see all the intermediate hops that your packet goes through. It doesn't just go directly from your computer to the other computer. It has to go through some intermediate computers along the way. And so once it leaves our server, it ends up on this computer 1.3 milliseconds later. And then it ends up on this computer about 6 milliseconds later. And then this is still in the data center. And then finally, it makes its way out of the data center, and it looks like this is already maybe the hop all the way across the Pacific Ocean, because you can see the difference in time. This one here was half a millisecond. This is already 136 milliseconds. And so once it does that, then it finally makes its way over to the other server. And so Traceroute tells us that it takes about 136 milliseconds, and then it takes 9 hops through all these intermediate computers and routers along the way in order to get from Fremont to Sydney. So going through those 9 computers at half the speed of light, I think, is pretty good. But that's 186,000 miles per second in a vacuum. The data is not traveling through a vacuum. Most of the time, it's traveling through a fiber optic cable. It's traveling through glass. So how fast is the speed of light in glass? Let's see. They say take the speed of light and divide it by 1.4682 to get the speed of light in a fiber optic cable. So if we do 186,000 divided by 1.4682, that'll give us the speed of light in fiber optic cables. So 186,000 divided by 1.4682, and we get 126,685 miles per second in fiber optic cable. So now we're looking at comparing 80,000 miles per second to 126,000 miles per second. And so we're a lot closer. Now we're more than half the speed of light. And so, I mean, that's just mind-blowing that it goes that fast. All the way across the ocean and all the way back. So I guess the point there is the internet's pretty fast. That, you know, we've come so far since what I was showing you last time with serial cables traveling at 300 bits per second, not even just 30 years ago, to an internet now that's going at, you know, 3/4 the speed of light all the way around the planet. It's just mind-blowing how fast things are now. So that's basically your final assignment. It's really pretty easy. You're just using some of the concepts that we learned over the last week about making a connection to another server and then sending a packet of data out and then receiving a packet of data and then measuring the time. That's all you got to do for this assignment. Pretty easy to do. And I have set up servers in 5 places around the world. That's one of the nice things about these virtual servers, is that you can just go to a website and say, I want to rent a server for 2 weeks, you know, and put one you know, at your data centers scattered around the planet, and just set it up and away you go. And so in about 2 weeks after the semester ends, I'll just take those servers down and we'll be done. So that brings us to 10 o'clock. What do we do for the remaining hour, hour and a half? And so I had an idea. And this is just going to be, I'm going to kind of wing it because I didn't prepare too much for it. I did do a little preparation over the weekend. And here's the idea I had. Is you may be familiar with this game everyone seems to be playing, called Wordle. And the goal is to guess a 5-letter word, and you've got 6 guesses to do it. And when you play a word, when you guess a word, the game will tell you which letters you got into the right position, which letters are in the word but not in the right position, and which letters are not in that word at all. So we've got to guess a 5-letter word, and we got to put in a first guess. Now, I don't know what the word is, and I don't think this is not the official Wordle game. This is not the one run by the New York Times. So I've already played that one today, so I already know what today's word is. This is a randomly picked word out of their list of words, and let's try to guess what it is. So we got to guess a first word. What would be a first word you want to guess here? And if you've never played this game, a good strategy is for your first word is you want to pick one that's got like, you know, fairly common letters, but no repeats. Does anybody have a favorite first word that they play on this? I can see your son there. Can you suggest a word for us to play?
How about house?
House. Okay. So it comes back and it says the letter H and the letter S are in the word, but those are not the places where they're supposed to be. And the letters O, U, and E are not in the word. So we need to come up with another word that has both S and H, but not in those positions, and that does not contain these other letters. So I'm going to guess that this word probably begins with SH. Notice that the S is no longer in the H position, and the H is not where the S is, right? So this is a good, maybe second guess, and then we just need to fill out the rest of the word using letters that are different than O, U, and E. What do you think?
How about shift?
Shift.
So
Okay.
IFT.
Good. So this letter is different from all these others, and so is this one, and so is this one. All right, this is good. So now we know the S goes in this position. And we also know that the word contains the letter H, but it does not go here. And also contains a T, but the T does not go there either. Now, here's where you have to start using your knowledge about how English words work. Like, we would probably not have the T next to the S, because I can't. Well, actually, that could work. I was thinking like that's not going to work, but yes, there are some words that begin with ST. So maybe that's where the T goes.
Or the TH could be at the end.
That's true. It could end with TH. So we know the T is not going to go here, so it could possibly go here, could possibly go here, could even go in the middle. We also know the H does not go here, so I think that might be a good guess that maybe it ends with TH. Someone suggested shout. So it can't be shout because we know that it does not contain O or U, and the T can't go in the last spot. This is where you maybe start playing around with words. Like maybe it's like SP, maybe A. No, it's not obviously spath, but this might start like getting your mind going about what the word could be. Pretty sure that the vowel we're missing is A, right? Because it can't be an O, can't be a U, can't be an E, can't be an I. The other possible vowel it could be is Y. Maybe there's a Y on the end. Is that a word? Swath? There's no E on the end of that, is there?
I don't know.
Let's go with that. That was it.
That was a good guess.
Well, I just started running through letters in my head, like, SB, SC, SD, and I just started playing around. But sometimes you do get lucky on that. Okay, so that's basically the Wordle game, is the computer picks a random 5-letter word, and then it's up to you to try to guess it, and then as you make the guesses, it tells you whether you got the letter in the right position, a letter in the wrong position, or a letter that's not supposed to be there at all. And so what I did over the weekend was I wrote a Wordle server. And let me show you how the Wordle server would work if we are just talking to it directly. If you remember, I showed you a program last time called NC that just establishes a command line connection to another computer that's listening to a specific port, and then you can talk to it, not audibly talk to it, but talk to it by sending it commands and seeing what responses it gives back. So this server understands a few basic commands. It understands quit. So if you just type in quit, it just closes the connection. Oops, I'm sorry. Let me see what happens here. It was let's see. I actually was supposed to say this right off the beginning, right at the beginning. It was supposed to say "See Wordle," so I'm not quite sure why it said that. But let's try this anyway. So you can type in a guess. So at this point, it has already picked a word. All we have to do is just start guessing what that word is. So let's start with, what was the word that you picked first? House. Let's do that. House. Oops. Something's not working here. Oh no. This is not working the way I intended it. Something is not right. Hold on. I need to go look at this. Oh, I got the password wrong. There it goes. What happened here? Incidentally, I wrote this program in a language called Perl, which is actually one of my favorite languages for just whipping out something really quick and easy to do. And so again, I was working on this over the weekend. And so what it should do here, let's see. Should load the word list, load the validation list, pick a random word, start the game. And then this here gets it to read a line from the input, right here. So it should have printed the status out immediately, and it didn't. Well, let me try it this way. Huh. How bizarre. This is what happens when you just like whip up a program over the weekend and you don't test it really well. Oh, I know what I need to do. Is it, oh, I know. I'm going to look at one of my other programs. Here we go. This one. That should help. There we go. That's what it's supposed to do. Okay, let's put in our guess. House. And it's telling us that this is guess number 1. And we got the H in the right position. We got these 3 letters in the wrong position, and we got this letter in. This letter is in the word, but not in that position. So because we don't have colors, it has to send back the information kind of encoded in a way that a client program could read that in and do something with it. So this is a simple back-end communication between the client and the server. The client's job is to present to the user interface and then translate the guesses into what the server needs, send that information over to the server, get the response back, and then present to the user the response, but colored appropriately. So let's make another guess. Let's see, it has to start with H and has to have an E in it, but it doesn't have an O or a U or an S. So how about, gosh, I don't know. How about I was going to say Helms, but it contains an S, and we know there's no S in there.
How about heart?
Heart. H-E-A-R-T. Okay. Okay, so we know there's an E and an A, but they're not in those positions. We know there's no O, no U, and no S. How about H-A-E? That's not a thing. That's not a thing. H, I. Well, let's go with HA maybe. HA. I'm just thinking about what letter could come. HA, not S. HA, what letter could come next? HAM, ham. Tony says, just try horse. Let's just try horse. Let's see what it says. No. How about H A L? Well, anyway, you get the idea, is that it's going to send back 2 words. It's going to send back a number, which is the guess number, and then a code about how the letters matched up. And so what we're going to write here is a very quick little Wordle client, and let's just see if we can kind of get it to do something. Okay? So how are we going to start this? Let's see, we're going to need standard IO. We're probably going to need the other, standby, standard lib.h. I know there's going to be stuff dealing with strings, so let's bring in string.h. And we'll need lib socket. What did I put it there? Lib socket. I don't remember now. Lib inet socket.h. And then we'll see what else we have to bring in. Okay, so the way this program is going to work is we'll start out by make connection to Wordle Server. And then we're going to go into a loop where we ask the user to type in a guess. Send the guess to the server, and then get response, and then decode the response and present a response to the user using colors. And then go back and do the process over again. So I'm putting these comments here as kind of like a to-do list. These are the things I need to do. It may not be complete, but it just kind of gets my ideas down about what has to be done. So let's start by making a connection to the server. Let's see, how'd that go? Int fd equals, don't remember now. What do I do first? Create inet stream socket, was that it? Oh, let me look at client over here. This has got it. I'll just copy this stuff. Here's the name of the server. The port number is going to be 5678, and the rest is the same. And then we're going to say if fd is equal to -1, that means it didn't work. We will printf stand error can't connect to server. And then print out an error message, and then we're done. Okay, instead of going into a loop, let's just prompt the user to enter a guess. We'll send that to the server, get a response back, and then just print it out on the screen, and then start iteratively kind of refining it from there. So prompt the user, have them type in their guess, and we need to strip off the new line character. Okay, and then we'll send that to the server. Oh, actually, after opening this, we need to convert that into a file pointer. So we'll go file pointer socket equals fd open fd and for reading and writing. Okay, send the guess to the server. So we'll go printf socket %s and my new line character. And then we get the response. The response is going to be pretty short. Let's do, well, let's just do 100. So I'm going to read the response in as one string, but I know it's composed of two parts. It's composed of a single character at the front, which indicates either the turn number, or actually the way the server is written is it could also be a letter indicating whether you've won or lost the game. So there's one character at the front, and then there is that 5-character code on the end. So we're going to use scanf, I guess, to break that apart into the two individual pieces. So we got a single status code, and then we have a string that represents the, the rest of the response. So I guess that would be the, what do we call that? It's basically this, right? I want to call it the answer. I want to call it the, well, let's, I almost want to kind of rename this here. Here's what I'll do. Let's get rid of this. Let's recycle the line string, or, yeah, let's go character line 100, and then we'll go response. That. Okay, now we're not going to decode the response, and all we're going to do for debugging purposes is just print that out. And then let's just see if that works so far. Oh, what did I do wrong here? Printf, oh, this should be fprintf. Let's see if that fixed the problems. And then I need to link to socket library. Hey, here we go. What's our guess? Let's do house. Oh, I forgot. when you first make a connection to the server, it immediately gives you a greeting, right? So after we connect to the server, we need to get greeting from server. So we'll use character line 100. And really all we need to do is just get that greeting. There's nothing we have to do with it. It's just basically to let you know the server is up and running. So let's just get that line. And then we're ready to go. Oh, we're using line several times here. So let's come down here. We're not going to need this. There we go. Hey, so we sent our guess over to the server and we got a response back. And here was the response. So what happens if you talk to the server and you actually guess the word, or you don't guess the word? So let's try talking to the server again. And let's just guess house, and it comes back with that. And let's just guess some other words. I just want to get to the end. So let's go heart. Let's go adore. I can just go adore again. And then I can do shirt. And then I could do one last word. Let's do house again. And then here, it comes back and it says L. Whoops. It says L. That means you lost. At that point, you can just quit. You're done. Let's try again. House. You know what? There is actually a. I put in some cheats on the server because you're sitting there debugging this thing. You're like, do I actually want to play this game? Like, how do I know whether I won or not? And how can I get to the winning state as quickly as possible? So again, I put some cheats in there so that it can actually tell us what the answer is. It says here, the answer is gloat. That's what we're aiming for, right? So what happens if we put in gloat? It says, we know this is a win because it came back and it put all the letters in capitals. Okay, so we know we won if all those letters come back being capital letters. If there is not any capital letters in there, or if it aren't all capital letters, then we know we haven't won and we need to go back and ask for more guesses again. So let's see if we can start decoding the response. So first we want to check to see if we won. Did we win? Yes, if all response letters are uppercase. So let's quickly go through and just see if we got all uppercase letters. So what we'll do is we'll set a flag called alt upper to initially be 1, and then we'll run through that string. And we'll check to see if any of the letters aren't an uppercase letter. And if they aren't, we'll set that to 0. And then we know when we get to the end of the string that we got at least one letter that was not all uppercase. So if response I is basically not an uppercase letter. So if it is not, or actually if it is less than a capital A, or response I is greater than a capital Z, then we know it's outside of the range of capital letters. Then set all upper is equal to 0. So at the end of this loop, we'll just look at the value of all upper and know whether we won or not. So if all upper you won. Okay, so if we established that we haven't won yet, now we need to do something with those letters. So basically, anywhere where we have a capital letter, we're going to want to print that in green, and anywhere where there's a lowercase letter, we'll want to print that one out in yellow, and anywhere where there's a dot, we'll want to print that letter out in, well, just not colored at all. So you've noticed here on the screen that some of these characters are actually colored, right? So we do have the ability to color things. How do we do that? So a long time ago, when people were using these serial terminals, kind of like I showed you last time, they wanted the ability to, once color displays came out, they wanted the ability to actually display things in colors. And so a group got together and they came up with a standard for characters that you can send over a serial line that will tell the terminal on the other end to color the text. And so these are called the ANSI color codes, or the ANSI escape codes. ANSI stands for the American National Standards Institute. And so they came up with these strings that you can send over a serial line that will tell the other end to change the color of the output. And so I think the way this works is every single one of those codes starts with an escape character followed by a left square bracket, and then some subsequent characters. And there are characters for like moving the cursor around on the screen. So in addition to the colors, you've got cursor movement and erasing characters and scrolling the screen up and down. But what we're looking for is changing the color, which I think is down, down, down here, colors. We've got a few basic colors. I got green right here, and I've got yellow. So these are the ones I want to use. And so we've got these numbers that we send, depending upon whether we want to change the foreground color or the background color. So the way this works is you send an escape key, followed by the left bracket, followed by the number 1, and then a semicolon, and then the number corresponding to foreground color, and then I guess the letter M, and that should change the color. And then you can also reset things back to normal. To reset colors, you send escape 39 semicolon 49M, or to reset all attributes, escape bracket 0M. So that's probably what we want to use. So let's write a little test program to see if we can do that. So we're going to send the characters corresponding to the escape, the left bracket. Let's change this, maybe let's do like green, right? So it would be escape, left bracket, 1 semicolon 32M. So we need to send the escape character. Now in strings, I believe escape is represented with a \E. Then we send a left bracket, 1 semicolon, and what did I say? 30, 32. And then this should be in green. And then an escape, left bracket, 0M, and that'll reset things back to normal. And look at that. That text is in green. Let's change it to a different color. Let's do red, which is number 91. It says this should be in green, but it's actually displaying in red, right? And we can even put different colors on the lines. So we could maybe switch to green and then switch to red. So let's do this. Let's go define green to be escape, bracket 1, semicolon. What did I say it was? 32. And define red to be escape, bracket 1, semicolon 91M. And define reset to be escape, bracket 0M. Like that. And then we'll do it like this. Ah, seems to have worked. Actually, it wasn't in red because what happened here? Oh, green, red. There should be green reset. Oh, red reset is what I wanted. There we go. So I could define a whole bunch of colors in my program, and then just be able to switch the text colors as I see fit. Oh, we also have bold. I don't necessarily want bold. Well, we'll go with that for now. Okay, so let's put that in my program. Oh, comment here is awesome. I was looking for a way to change the color for my C program to-do application. So there's how you do it. Pretty easy, huh? You just send those sequences and it just changes the colors. Okay, so let's see if we can get it to actually decode the response and change the colors appropriate. So we're going to run through the response, one character at a time. And then look to see whether it's a capital letter or a lowercase letter. So if it's a capital letter, we'll display that letter in green. If it's a lowercase letter, we'll change it to capital and then display it in yellow, and then we'll handle the dot here in a moment. So if response I is a capital letter, and it turns out there's actually a function built into C, or the standard library, that will tell us whether it's a capital letter or not. It's called isUpper. And all it does is it just does this kind of thing. Oops, sorry. It does this kind of thing. It just checks to see if it falls within the range of a capital A to a lowercase a, capital A to a capital Z. That's all it does. It's just built in for us. So if it's a capital letter, then we're going to print that letter out in green. And then else, if is lower, response I, then we're going to print it out in yellow. But we're not going to print, well, initially, let's go ahead and change it. We're going to change it from a lowercase letter to an uppercase letter, and all we have to do there is just subtract 32 from the ASCII value. Else, we know it's going to be a dot, and so we're going to print out let's just print out the dot for now. And then finally, when we're all done, we need to print out the reset character so that we go back to black. Okay. So is upper comes from some header file, and I'm hoping it will, oh, no, I'm hoping it'll tell me what that header file is. ctype.h. Nice compiler. Tells me what to include in order to get that to work. Oh, and I didn't put in yellow. So what is the escape code for yellow? It is 93. Okay, what's my guess? Let's do house. Uh-oh. Oh, it just went dot, 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 dot. Oh, why did it do that? Okay, first of all, we don't want it to print out just the raw response. Actually, let's have it print out the raw response. Oh, it's because I printed out a new line here. I need to do that after the whole loop is done. So this needs to come out and go over here. And then the new line character. Okay, let's do house again. Hey, pretty cool, look at that. All right, there's my letter in yellow, or as best as it's going to get on this screen. Let me see if we can get something that's better. So it's actually not this yellow, it's kind of like, see, the problem is that you send this color changing sequence of characters, and then it's up to the other end to really kind of like interpret what color should actually be displayed. So you can send the character for green, but you can see that, you know, what green you actually display depends upon what operating system you're running. So I don't know, that's probably the best we're going to do for now. It's good enough, at least for getting things going. Let's try that again. Let's put in house again. Oh, that had no letters at all. Let's put in train. Nothing. Let's put in train again. Oh, there we go. So we got T and the I. They're in the wrong spots, but they are in the word. So the last thing I want to do is I want to print out these letters in black instead of the dots. So what we do there is instead of printing out the response, what we do is we print out the original guess that we had typed in, which is sitting up in guess. There, that's what I want to see. So these are in black to tell you that these letters are not there. These are in green. This is in black and this is in green. That's perfect. So now we just have to like wrap all this stuff up. And I can see that my main is getting longer and longer and longer. So we would start at this point thinking about breaking it up into separate functions. But well, we'll do we'll do that in a little bit. So we'll say while not winner, while not, let's say while not game over. Actually, this will be a do, won't it? Because we're going to do this at least once. We'll do it like this. While not game over, and let's make a variable. Int game over equals 0. Then all this stuff here gets indented, and then we go here. Okay, what's our guess? House. Oh, I guess at this point we no longer need to print out the response, but let's go ahead and keep playing the game. So we've got E in the right spot, we've got S in the wrong spot, and it doesn't contain H or O or U. What's our next guess? Maybe let's do Spire. Ooh. Okay, so we got S, I, and E in the right spot. We just are not going to use P or R. How about like SWI? I was going to think of swipe, but it can't be that because there's no P in there. So how about swine? Here we go. Ooh, okay. So S T I oh, someone said shine. Okay, it can't be shine because we know there's no N in the word. But I think you're on the right track. S-H-I, shive? Is that a word? Shide? No, it's not that. Whoops. I don't think it's going to be that. It's not going to be shire. Maybe it's not SH. Maybe it's S-T-I. Stife? Stime? Style? Is stipe a word? Let's try. Oh, that's not a... Oh, so one of the response can actually be the word invalid. So we would have to handle that a little bit later, but. How about slice? Ah, it's not that either.
How about Spire? S-P-I-R-E.
It was actually one of the ones I played.
Oh, is it? Okay.
Yeah.
Oh, you're right.
Snide? Snide? It's not that either. You're so close. Oh, what could it be? SKI? Is that a thing? We know it's not an N. We know it's not a P. We know it's no R. We know there's no H. Did I try that? Oh, I didn't try SH, but I couldn't think of a word that would fit that. That didn't have. It can't be Shire, right? Because we've eliminated R's, and I don't think that's a word. Shide, Shige, no. Shile, I don't think that's a word. Shime. Oh, how about shine? Oh, I've actually, we've already eliminated N, so we know it can't be that. Shive? Shipe? No? All right, well, let's just guess. Let's just guess some word. How about style? Is that? Oh, hey. Okay, so now we know a T goes there because it can't go there. So it's S something ITE. And I'm pretty sure, did we try swipe? We tried swine, and we know it's not that. We know there's no W. So S something ITE. And then it's not spite. It can't be Shire because we've eliminated R. Shipe. You think that's a word? Shipe? Actually, but now we know there's a T here. We know there's a T.
Have we eliminated M? Could it be smite?
Smite? It was game. Well, actually, this is it saying game over, right? So we didn't get it. But smite was a word. Smite was a guess. Actually, let me take out the printing out the response. We don't need that anymore. Okay, well, at this point, we're well on our way to making this game. So there's a server sitting on a remote machine that is accepting our guesses, and then it sends back a response, which tells us the turn number, which we're not doing anything with, and an encoded answer about whether the letters are in the right spot, the wrong spot, or not there at all. And then the client needs to take that response and turn it into something that the user can interact with. And this is how most things like applications on your phone work. is that when you say bring up the weather forecast, the server doesn't send you the picture that you see. It sends you just the raw data. It might send you the high temperature, the low temperature, the wind speed, barometric pressure, current conditions, like is it cloudy or sunny. And then it's up to the weather app on your phone to take those numbers and to take those encoded results and turn it into the pretty picture that you see on the phone. So embedded in the application on the phone will be the icons for displaying the current conditions. So the response comes back as the word sunny, and then your phone app needs to turn that word into a picture of sunny weather. It's up to your app also to present things like the temperatures in a way that you can understand. Maybe it makes the high temperature and the low temperature like physically bigger on the screen, or it might display some kind of graph showing you the temperature variations through the day if it receives all that information from the server. But my point there is that the interaction between the client and the server is very terse, very short, just enough data is being sent so that the client can then take that data and turn it into the user interface that the user sees. Abdul asks, you mean this is called an API? And that's exactly right. This is called an application programming interface. That behind the scenes, there are the actual, it's almost like functions and methods, is that a library of code will present to you some functions or methods that you can use, and then you need to assemble those functions and methods into an actual working and program. So you wrap all those function calls up with things like prompts to the user and displaying the responses back to the user. So an API can take the form of functions and methods to call, and can also take the form of commands to send to a server and receiving the response. And it has to be documented somewhere what those responses are going to look like so that you can decode them correctly. If I had typed up documentation for my Wordle server, I would have said the response is going to come back in the form of a single character, which contains the turn number, and then the response. And I would also document other things that it could send, like game over or invalid. And we would have to have code in our application, our front-end application, to deal with those responses. So that's typically how internet applications work. Whether it's a weather app or Snapchat or Facebook or Discord, is the client presents to the user a pretty interface that the user deals with, and then turns your interactions into requests that are sent to the server. The server responds with answers, and then the client then presents those answers to the user in a way that's meaningful. So you noticed in a program that we wrote here, we started out by just displaying the raw response from the server, and then went on to refine things to convert that response into something that the user likes to see with the colors. So I'm kind of answering Abdul's question here. So I'm modeling this server kind of on the way that older internet servers worked, like mail servers, in which you send your responses with a command and then some kind of option after it. Like you might say, I want to send an email to this recipient. So you say recipient and then the email address. And you might say it's from, and then an email address, and the subject, and then the string representing the subject. So you have this two-way conversation with this server consisting of a command and then some options with that command. And you get a response back to letting you know whether that command was accepted or if it was rejected. These days, a more modern approach would be to send a request in the form of a structured document, like what's called a JSON document, which stands for JavaScript Object Notation. It's a way of sending data in a structured manner that can be decoded by the other end and turned into strings and arrays and dictionaries fairly easily. And then the response would come back from the server also as a JSON document, or it can come back as XML or HTML or something like that. But anyway, you get back a structured document, not just a single line of text. But the way I did my server here, I'm just using single lines of text because it's easy for someone who just knows about using printf and fgetS to be able to interact with the server. We don't have to decode the JSON document. But I have done that in the past in this course. I have actually interacted with a weather server and then had you write a program to go and ask the server for what's the current weather in my current location, and it sends back a response, and then you had to write a program to go and decode that JSON document that it sent back and extract out the piece that represented the current temperature and the current conditions and the current barometric pressure and the wind speed and so forth. So, as you can see from our program here, we're on our way, right? We're using a very simple interaction with the server. We connect to the server, get our greeting, throw it away, and then we just proceed to have this two-way interaction with the server in which we send a guess and get a response back, and then we send another guess, get a response back, and so forth. And we have this two-way conversation. The server's job is to keep track of the rules of the game. So when you reach your sixth guess, it then stops the game at that point. It says, game over. We didn't do anything with that, but it does that. So it's not up to the front end to stop at guess number 6. It's up to the back end to basically enforce the rules of the game. The real Wordle, the one you can actually run on your app here, also has something called hard mode. And in hard mode, you are required to use letters that you've guessed correctly in your subsequent guesses. In easy mode, you don't have to do that. You can guess a completely different word. And so if you wanted to switch on hard mode, then it would be up to the server also to enforce that, to make sure that your guesses conform to the rules of the game. It's really important when you're doing things like online games like Valorant and Minecraft, that the server enforces the rules of the game, not the client. Because what could happen if the client enforces the rules of the game? Well, you get someone who mods their client so it doesn't obey the rules. And then basically you're cheating, right? Like, imagine if you had a game in which you had to collect coins, right, in order to be able to buy things, but it was up to the client to decide whether or not you could afford something. Well, that wouldn't work out really well, because if someone could change their client, make themselves as rich as they wanted. So if the client kept track of how much money you had, that wouldn't work, because you could always change that. So it's up to the server to enforce those things, to keep track of how much money each person has, so that when they try to buy something, the server either says, yep, you got that thing, or nope, you didn't get that thing. So that's kind of where we are right now. Hopefully you've got enough information to be able to do this last assignment. There are some videos to watch. If you're in my class, you can watch. Those videos came about because this happened about a year ago. I went on the live session. I did my whole presentation about how to do the assignment, how to create connections, send your request, get your response back, how to measure the round trip time. And then at the very end, I said, oops, I forgot to hit record. And so that afternoon, I had to go back and record a whole series of videos. It was nice because I was able to condense it down to about 20 minutes. But those are the videos that you can watch on the website that walk you through the assignment. And then that's basically it. So what's coming up over the next couple of weeks is we have week 15 next week. And then we just have a couple of days where we can do question and answer about any assignments that are so lingering. And also, if you're watching this after the recording was made and you can possibly join at our usual live time, that would be a good time to get your questions answered. There's nothing I love more than having a student come on and say, I'm having trouble with my program, please help. And then we bring it up on the screen and we start debugging it. And not only are you and I debugging it, but also your classmates are also helping out to debug it and find out what's going wrong. And that's a really powerful way of, I think, going through and problem solving, because you get to hear not only just my perspective, but also your other students' perspective on what's going on. And they get to see that, hey, I'm not the only person who has problems with the program. If you're having a problem with a program, chances are somebody else is having a very similar problem, and they would like to hear solutions to that. So if you possibly can, and you want your questions answered live, then hop on next week, and we'll do that. If no one comes and asks questions, then we'll figure out what to do. We'll fill up the time with some other programs to write. I'm thinking maybe one of those days we will write a quantum computing simulator. So if you watched my recording yesterday, that was in my discrete structures course, not the C programming course, but the discrete structures course, then we did a quick introduction to quantum computing and worked out some of the math behind it. It would be interesting then to write a computer program that does those same calculations and shows you that you can simulate a quantum computer in a classical computer in a very, very limited sense, right? We're not going to write anything really complicated, but to actually show you that you can actually do the math in a computer program and simulate the results of an actual quantum computer. So that'll be, either Tuesday or Thursday next week. And then on the 16th week, we'll be doing our quick Zoom meetings to come at a consensus about what your final grade is. And so next week I will have a grid where you can sign up for a time slot. There will be lots of time slots available during that 16th week. And you just find one that works for you. Come to those meetings with your assignments completed as best you can and that survey filled out so that we can go over the results during that quick 5-minute session that you have with me. So are there any questions before we end it for today? Chris, anything from you?
I don't have any questions, but that was really interesting.
Oh, about the program we wrote?
Yeah.
Good.
Oh, I will say I did the round trip assignment last night.
Uh-huh.
And I was stumped for a while because I thought I'd make a communication out to the server and then it would just hang it wouldn't do anything. And man, I went around troubleshooting it for so long until I realized I wasn't sending the new line character.
Oh, yeah, it's really important to send that new line character because otherwise the server just sits there and goes,
yeah.
It's kind of like calling, it's literally behind the scenes. It's just calling fgetS, right? And your program just hangs until you press enter.
Yeah. So
just like your regular program. So the server does the same thing.
Simple solution, but man, that was difficult to see.
And I'm so glad you did the program after I got the servers up and running because I was madly putting those things together last night, hoping that no one had begun their assignment yet. And it looks like you did it after I got those up and running. Because I thought you were going to say like, hey, I was writing the program and like it didn't work. It kept crashing. And
I figured Fremont would work at least.
Yes, right, because we've been using that.
I started with that one and yeah.
And of course, the Fremont server is right in the same data center as our development server. So those times ought to be really quick, right? Probably less than a millisecond.
Yeah, they're fast.
Did you try it out with the other servers?
Yeah, I've done all the servers.
I'm interested to know what you got.
Fremont was 0.34 milliseconds.
Mm-hmm.
London was 130.29 milliseconds. Mumbai was 279.42 milliseconds. Sydney was 137.09 milliseconds. And Newark was 68.68 milliseconds.
It's interesting that Sydney, you got 137, and when I ran the program, and admittedly it was last year when I did that one that's in the assignment, it was 182. So it's gotten faster.
Yeah.
Since then, so they must have laid a new cable down, and maybe made one that was a bit, a few less hops, or just somehow faster than the old one. So it's gotten 50 milliseconds faster since the last time we measured it. So obviously Fremont is the shortest because that one's in the same data center. Newark is the next in line because that's just simply on the other side of the United States, and that's what, about 3,000 miles away? And then Sydney and London are both roughly the same distance. Actually, London is what, 5,000 miles? And then Sydney is 7,000 miles. And then India is pretty much on the other side of the planet from here. So I would expect that one to be the longest. But for those of you who are scattered around the planet watching this and able to compile and run this program on your own, you'll get different answers because you are physically located in a different location. So if you're in Europe, your round trip time to London will probably be the shortest one, and you know, the one maybe to Fremont might be the longest one. Yeah, so it takes more time to respond just because it's further away. It takes more time for the data to physically travel from one side of the planet to the other. Let's go ahead and, what's the distance from Fremont, California to Mumbai, India? Well, not too bad, 8,400 miles. But that is, of course, you know, roughly a straight line. It looks curved here, but the planet is curved, so this is probably roughly a straight line. But it's not really going to probably take this route. It's not going to, you know, go there and then go straight across China. It's probably more likely going to take, you know, a more circuitous route to get there. So the actual route will probably be a bit longer. And the round trip times can be influenced not only by the physical distance, but also by the speed of the cable. Like, you know, just at home, you have Ethernet cables, but some of them might be carrying a gigabit per second, some might be carrying 100 megabits per second, some might be as low as 10 megabits per second. And if the cables become congested with a lot of traffic trying to flow through that one cable, then data has to slow down. Data has to wait before it gets a chance to get on the wire and go to the other end. Same thing happens with these transoceanic cables, is if you've got, let's say, a single connection between California and Japan, for example, and there's a lot of data that's trying to go down that pipe, you know, it's kind of like cars waiting to go into a tunnel. There, you know, there's only one lane through that tunnel, and if you've got a lot of traffic trying to go through that tunnel, just cars start piling up until they can get in line and go down to the other end. Once they get into the tunnel, it's a straight shot. They just got to wait to get in there. So same thing can happen here, is if you've got a either a slower link or a congested link between 2 points, then data has to wait, and that could also cause these round trip times to go up. So that one to India, I can see is, you know, roughly twice or half the speed as the other ones, but the distance, according to this, is not that much further. So what would account for the difference? Well, it could be that the link itself is a bit slower, or it's more congested, or a variety of factors. So, you know, another interesting thing to do would be to run these tests at different times of the day. Certain parts of the planet get more busy during times of the day. You know, here in the United States, the internet tends to get pretty busy during the daytime hours, and it gets quieter at night. And those graphs have actually changed over time. If I can plot time, where maybe this is, you know, 0, 0, this here is 12, and this is 23, right? It basically, you know, it goes like this, right? So people start waking up, going to work here around 7, 8 o'clock, and then there's a peak in activity around noon, and it starts dropping off around 5 or 6 o'clock at night when people start going home. And that's what it used to look like. But nowadays, it's probably a little different. It's probably still, you know, the ramp up during the morning hours, and then it comes back down, you think, and then, you know, there's another little loop there as people get home and they start streaming their movies. So things tend to get a little bit busier in the evening hours after dinner's over, when people turn on their Netflix and their, you know, Amazon Prime, and they start watching their videos, and so you get another spike in the usage. And then it falls off again as we enter the night hours. Question here is, does the internet still use cables under the ocean? Absolutely. That's probably the most reliable way to do it. You might be thinking, why not just use satellites? Well, the problem with satellites is it has to use radio signals to, you got your planet here, and you got your satellite out here. It has to use radio signals to send a signal up and then get a response back. Well, you've got a couple of problems here. One is this distance is enormous. This is about 20,000 miles up to geosynchronous orbit. I think that's about right, which means the round trip is 40,000 miles. So if you thought your round trip time was terrible with just going 7,000 miles, think about going 20,000. So already you're tripling the distance that it has to go. So your ping times are necessarily going to go up. And the other problem is since you're using radio, all the traffic has to share these radio frequencies that are being used. So that means there's going to be a lot of congestion on those satellite links going up and down. Whereas with a cable running under the ocean, I was trying to draw this picture here. With a cable running under the ocean, if you want to increase the amount of data flowing through those cables, you just lay a new cable. And so actually, these cables are really small. They're maybe like only a millimeter thick, and with today's technology, you can send gigabits of data per second through just a single cable that's a millimeter thick. But of course, if you laid a cable that thin through the ocean, it would instantly break because of ocean currents and anchors going through. So they actually bundle up those fiber optic cables inside of an armored sheathing. So the whole cable is probably this big around, and the actual data is flowing through a very tiny cable right in the middle of that. And it's all wrapped up with steel and rubber around it to provide water resistance and physical damage resistance. But you don't just lay one single fiber optic cable. If the expense there isn't actually hiring the boat and spooling all that thousands of miles of cable up and laying it all down through the ocean, that's the big expense. The expense itself is not in the cable. So you don't just lay one, you might lay 100 of those in one single cable. And then once you got both ends connected, you then start sending data through one of those fiber optic, not wires, but cables. And then as that one starts becoming more congested, you light up the next one. And now you've just doubled your bandwidth. And as that one becomes congested, you light up the next one. And so over time, you're able to increase the amount of bandwidth that you're using by just using more and more of those fiber optic cables. And so with a satellite, if you want to double the bandwidth, you got to launch a whole new satellite and find a frequency that you can use and deal with the distance being traveled. Whereas with a fiber optic cable, you just lay a new cable, or you just light up an existing cable. And then, boom, you just doubled your bandwidth. So, yeah, cables are absolutely used these days. Some internet links still use radio, and those are used for really short distances. And I'll have to tell you, there is... I don't have to tell you this, but it just kind of triggered something in my mind here, is people who, like stockbrokers, people who deal with trading stocks and securities on stock exchanges. Back in the old days, it was done by people physically in a room. And if somebody had some shares to sell, they would like put that up on a board and say, I've got 100 shares of company XYZ to sell. And then people down on the trading floor would be on behalf of their clients, would then start, waving pieces of paper around saying, I'll pay $50 a share for that, or I'll pay $58 a share for that. And then basically it goes to the highest bidder. And that's how stock prices are set. But these days it's all done by computer. So instead of physically putting a piece of paper up on a board saying that I got shares to sell, now you just type it into a computer that I've got these shares to sell, and then other computer programs are listening for those sell requests, and they respond to those with purchase requests. And this all happens now in a fraction of a second. Now, think about an eBay auction. It only takes a millisecond to execute from beginning to end. So this is called high frequency trading. The trading now happens in just milliseconds rather than seconds or hours. Well, if you want to be a high frequency trader and you want to get your first bid in, it means you've got to have a computer that can respond to those sell requests as fast as possible. So you want to have a computer that's listening for those sell requests, and as soon as one comes in, you check your database to see if you have any clients you want to buy, and then you put your bid in as soon as possible. And if you are the first person to put your bid in, then you basically control that auction. Well, we've already seen that the internet goes pretty fast, right? These computers that are acting as intermediaries for your data packets are already running at almost over half the speed of light. So really, high frequency trading in today's world is governed by that round trip time. If you are physically closer to the stock exchange, you've got a leg up on someone who's physically further away, just because your round trip time is going to be faster. That's just physics, right? There's nothing you can do about that. And so one example would be in downtown New York. You've got the New York Stock Exchange, where billions of shares are bought and sold every day. And then so you've got this building where the New York Stock Exchange is, and then around that building, close by, you've got these old warehouses and old hotels that are being gutted and replaced with computer and network equipment that are just across the street from the stock exchange. You know, they're just like 1 block away. And if you're that close to the stock exchange, you've got first access to those sell requests that come out, as opposed to someone who's 10 blocks away in some office building somewhere else. If you are physically closer, you've got access to those sell requests before someone who's even 2 blocks away. But imagine this. You've got a building here. This is the New York Stock Exchange. And then you're over here, and you are a high frequency trader. And you've got your computer in here. You got the New York Stock Exchange computer, and then there's a fiber optic cable running between your computer and the New York Stock Exchange. So what's this distance plus this distance plus this distance? It's not much. It's maybe 1,000 feet or so, less than a mile. But you know what? It's 3 times longer than this distance. So how could you get a shorter distance between you and the New York Stock Exchange? Well, so this is where radios come into place, right? You put up an antenna right here. New York Stock Exchange has an antenna over here, and then you run radio signals between them. Still running at the speed of light? Actually, probably goes faster because it's going through air versus glass. So the speed of light is faster in air than it is in glass, and you got a shorter distance. So yeah, you're going to want to set up microwave antennas in order to get 3 times closer to the New York Stock Exchange than someone who's using fiber optic cables. What's the difference? Is it a difference between, the difference is now is down into microseconds. But for high frequency traders, that is all the opportunity they need. If they can just get their computer to get that sell request before anyone else, they win. So that's what's going on, in downtown New York right now, is putting all these microwave links up to the New York Stock Exchange so that you can be physically closer, and physically meaning shorter distance the data has to travel. So under the ocean, absolutely, use cables, right? It's more reliable. You don't have to launch a new satellite. If you want to increase your bandwidth, you just lay a new cable, or you use the fibers that are in the existing cables, and you're good to go. If you're using satellite, you got a longer distance to travel. Satellites, break down, and when they break down, it costs millions of dollars to replace them. And also, you have to use radio, and everyone is sharing the same radio spectrum. So you got your allocation, and if you want another allocation of spectrum, you got to, bid with other people to get that spectrum. And those spectrum auctions don't come up very often. Would optimization of the trading software make more difference than distance? Well, they certainly do that too. They try to get those trading programs to act as fast as possible. But all the other frequency traders are doing that too. They're also optimizing their programs. So it's kind of this this race to see who can respond to those sell requests first. And some of it has to do with writing programs that are faster, and some of it has to do with getting your offices closer. What do we got here? Lord Melbury says, Google has their own private fiber between continents. I wouldn't doubt it. I wouldn't doubt it. Always interesting stuff to talk about. But I think we've just about reached the end of today. I said that already, but now I mean it. So I'll let the Zoom folks go first. Hey, I hope you have a good weekend. Wrap up those programs as soon as you can, and then I'll be posting information about those Zoom time slots here in the next couple of days. Okay?
Well, thank you very much.
Yeah. Take care.
All right, you too.
Bye-bye.
Bye.
Let's see if I can catch up on some of the YouTube comments. I think Abdul's comment is more or less on the ball here, or on the what's the term there? You got it right, that if you want to do web development, C is probably not the best language to use. Really, if you want to do, if you're like Google or something like that, where you need to have your programs running really fast, and because you've got billions of requests, you might eventually want to turn your servers into C programs so that they can go as fast as possible. But for just general purpose web development, you use PHP or Ruby or JavaScript or any of the other interpreted languages out there, because it's good enough and it allows you to get your product and your service up and running quickly, as opposed to going as fast as possible, like having it performance-wise going as fast as possible. You want to get your service up and running so that people can start using it quickly, and those other languages are just great for that. So what you were hearing over these recordings and also the ones previous was an actual college course that I teach. So on Tuesdays and Thursdays I teach C programming, and on Mondays and Wednesdays I teach discrete structures. And so that voice that you occasionally heard was one of my actual students in the course, and we're interacting over Zoom. And on YouTube I'm just opening up all the content to anyone who wants to listen in and take part. Like I said, so what you hear and what I say is geared primarily for my students. If they ask a question, then I respond to them, and then I get around to the questions on YouTube. So there was one question about, can I recommend resources to start doing web development? And I think I'm probably not the best resource for that. I don't have I'm not like keeping, because I'm primarily teaching these other courses, the C programming course and the discrete structures course. I'll also be honest, I don't have like my finger on what's the latest resources to use to get into web development. That's just not my area of expertise. So your better bet is probably to talk to some of your friends or talk to some of the people on YouTube channels and find out what they say. Are there good coding camps to go to? Are there good online courses that you could take to get started on this? And what's a good way to kind of get going so that within a year or two, you're up and running, and you can do some very simple web pages and do some back-end database work pretty easily. I guess the reason why web development honestly doesn't appeal to me so much is that there's just so much to learn to get something to work. It's not like you can just use one language and be done with it. If you want to do web development, if you want to do what's called full stack development, you've got to learn SQL for database. You've got to use JavaScript for interactivity, CSS for styling things on the screen, HTML, and probably one of the middle languages like PHP. So there's already 5 languages you need to learn just to do something more than a trivial little web page. And to me, I know a little bit about all those languages, but I can see how for a beginning developer, that is just like an overwhelming amount of stuff to learn, because you really can't do anything interesting until you know all 5 of those languages. You can start out, of course, using HTML, but you won't get any interactivity. So then you have to throw in some JavaScript, and there's so much out there as far as JavaScript goes. And then you have to start talking to back-end servers. So there's your PHP, and there's your SQL for database work. And so it's just an incredible amount of stuff to learn. And me, I like to keep things simple. So command line, that's where I'm at, right? Occasionally I do web stuff, but it's really simple stuff. But you're right, all these fundamentals are pretty much universal. Loops, conditionals, variables, the output, input, that's all universal across the board. It's just actually the details about that particular language is where it differs, but the concepts are all the same. You're right. So web development always changes. You need to be keeping up to date all the time. But if you want to get started, you learn HTML, JavaScript, CSS, and then you can get going. And then you can start working with the live data on the back end. But still, it's a fair amount of stuff to learn. Where do you start? Because there's also this thing I think that happens with beginning students is they see websites that they've interacted with, like Reddit and Snapchat and Discord and all those, and then they look at what they're able to produce after a few days or a few weeks of work, and it's nothing like that. Right? If you're just using raw HTML, it's going to be simple text and some images and some links, and that's it. If you want to make it interactive and have little animations, then you got to start throwing in JavaScript. And it's kind of like, here's where I am and here's where I want to be, and I don't see the route to get from here to here, and the stuff that I'm producing now is just nothing like what I want to produce. You have the same problem with video games. It's like you look at a current blockbuster video game like Valorant or Minecraft, and you go this is a game I want to develop, but what can I actually start with? It's going to be like Space Invaders, or Pac-Man, and it's nothing like that, right? It's nothing like what you want to produce. And it's really hard to see, here's where I am, here's where I want to go, what do I have to learn to get there? And it turns out it's a lot. It's a lot of stuff. And of course there are libraries. For games, there are game development engines that you can download and use. And then for web development, there are web frameworks in JavaScript like React that Abdul's talking about, and there's jQuery, and but again, it's just a huge amount of stuff to learn. How to fit all those pieces together, and how to get to good enough where you're not just kind of like following recipes that you found on the internet. You find some website that gives you some answers. You copy and paste the code, and you put it in there, and you go I hope that works. Seems to work. And then someone comes up and says, I want it to work a little bit differently. How do you fix it, right? It's just, to me, it's just a lot of stuff to learn. So, not to discourage you. I mean, obviously it's possible. Obviously people do it. And so I'm just to give you my opinion, why I don't have a whole lot of information about web development, because I personally don't like it. It's just like I have other things to do. Yeah, and you're always keeping up to date. Always new versions of stuff coming out. Always new technologies. Always new frameworks to learn. And just keeping up with that is just this race, constantly running to try to keep up with the latest stuff. So, I'd say if you're a new developer, dabble in a whole bunch of stuff, find the thing that you're really interested in and become good at that. And then people will come to you. If you find your area of expertise, if you find something you're really good at, then people will find you. Or you'll find them. So rather than trying to become good at everything, become good at one or two things. Become really good at one or two things, and then make your career out of that. Writing apps and writing games is nice and flashy, and that's what people see, and gives you a sense of accomplishment if you can see people downloading your program. But someone's got to write the back end. Someone's got to maintain the servers. Someone's got to write the networking code. Someone's got to do all that stuff that no one ever sees. And if that tickles your fancy, if that's what really is interesting to you, do that. You can make a job out of that. Anyway, that's just me. So. Okay, I think that's about it for today. If there are not any last questions, then I will say goodbye, and I hope you all have a good weekend. And I hope you do well. Practice on your programming. Come back next week. We'll do some more stuff. Have a great weekend. I will say goodbye to Lord Melbury and Alexander and Abdul. And who else we got here? Anmol, Tony, Govardhan, Dylan, Ermin, all of you. Thanks for watching, and I will see you next week. Bye-bye.